Okay, let's start. Hello, welcome back to AP Physics C. For your response questions, this is the 2024 set. We're gonna do set 2 because we did set 1 last time. Let's just get into it. Let's read question 1. Blocks A of meshes M and 2M respectively are arranged in a setup consisting of a ramp that makes an angle theta with a smooth horizontal table. So that's this. In an ideal spring over here of spring constant K fixed to a wall as shown, block A is held at rest at distance D up the ramp, and block B is at rest at on the horizontal table. Okay, the coefficient of kinetic friction between A and the rough ramp is mu in the region of length D, and there's negligible friction between the blocks in the smooth table. So here there's friction because there's rough. It's rough ramp. It's a rough ramp. It's mu. It has mu, and then here it's frictionless. Time t equals 0. Block A is located at horizontal position x equals 0, and release from rest. Okay, so it's released from rest from here. And then after the block is released, the following occurs at time t equals t1. Block A has traveled a distance d down the ramp and has transitioned to the table and is moving with speed v at x equals x1. So it's gone from here basically to here. Okay. So at time t equals t2, block A is at x equals x2, okay, and collides and sticks to B. So they stick together and they collide. At time t equals t3, the combined blocks A and B are at x equals x3 when they collide and stick to the spring in its equilibrium position. Okay, so they collide with the spring and then it's gonna get compressed. And then at time t equals t4, the combined blocks A and B are instantaneously at rest and the spring is compressed at distance xc from its equilibrium position. So that's when it's max compression because it says instantaneously at rest. Okay, so for parts AII, these parts express your answers in terms of m, theta, d, mu, xc, and physical constants as appropriate. Derive an expression for the speed v of block A at times at time t1. So what it's asking us to do now is, okay, so here's t0, here's t1. So derive the speed after this goes down here, but it has not hit the block yet, the other block yet. Okay, so let's just think about what we need to do. Right off the bat, you should be thinking work energy theorem. Work equals the change in mechanical energy, right? But you normally, right, anyone would think conservation of energy, but in this instance, you wouldn't think conservation of energy, you would think work energy theorem, because friction is doing work and it's a non-conservative force. It'll dissipate energy. So let's think. So the work done by friction has to equal E final minus E initial, right? So I'm going to use this little symbol for friction the entire time. So if you see F, it's there. So friction work is a dot product, so I'm going to write F dot D. That's the dot product because work is force times distance, and the distance that friction is being applied is that distance D. And let's think about the energies. Well, what's the final energy? The final energy is kinetic energy. And what's the initial energy? The initial energy is gravitational potential energy. So I'm gonna write K final minus UG, which is our initial gravitational potential because it's up here. It has some gravitational potential and then it slides down here and it no longer has gravitational potential, just kinetic, right? But friction takes away some of that energy and slows down the block, or well, reduces its overall speed. So now we need to think, all right, so the dot product is going to give us F D, where F is the force of friction, cos FD cos theta, where theta is the not this theta, not this one. In this instance, theta will be the theta between the two vectors. So because friction acts like this way, but our displacement is this way, the theta is 180, and cosine of 180 is -1, right? So this is actually, I'm gonna write -1. This is actually negative FD. So now let's find final kinetic. Well, let's put in final kinetic. So it's 1/2, and the mass is 2m, not m. So we're going to have to take that into account. V final squared, so that's our kinetic energy. Minus, now here's where things get a little bit more complicated, but not so much. Oh my gosh. Okay. So it's mgh, but I'm going to put in 2m because that's the mass of block A. So it's 2m, g, and now this h. So this h, we're going to go off on a tangent over here and think about it separately. So I'm going to draw out everything here. So they asked, there's theta. So they asked for things in terms of m, theta, d, mu, and xc. So we're not given h there, so we're going to have to derive it ourselves. So let's think about, well, just trigonometry. Sine of theta is equal to opposite over hypotenuse. Well, what's our opposite? This h is our opposite. So h over d, because d is our hypotenuse. So d sine theta equals h. And then we can just leave it there, and then we can start working towards the next one. So we're going to sub in h with d sine theta and then rearrange this equation. So we're going to rewrite this. F negative fd equals 1/2 2m. And there's a reason I'm leaving that 2m there. You'll see in a second. Minus 2mg, and we're going to write d sine theta. So now we're getting closer, but now we need to sub in for friction because we're not allowed to leave it just like F. No, we have to find that. So, but we know that the force of friction is equal to mu, well, the magnitude, I guess, is mu Fn, right? And we're given mu, so we don't have to worry about that. We don't have to derive that, but we do have to derive Fn, right? Because we don't know Fn. That's not one of our things we can leave in. So we're going to do our sum forces on the y. So sum of the forces on the y direction. And remember, this y direction, I'm going to make this clear, is along this line, right? Not this line, this line. And the reason for that is because it makes things way easier when we're dealing with just like things on a ramp. We change our y directions and our x direction, so our new x direction is this way. But we change it so that it's easier to work with and we don't have to deal with the theta as much. But those are called new Cartesian coordinates. But you always think when we're on a ramp, we're going to change our coordinates. So the sum of the forces along the y that are acting on the block, I'm going to think about my free body diagram as well. So here's the normal force on the block. Here's gravity pulling it down. And here's friction. I should just stick to what I wrote. So there's friction. So this is G. So the only forces on the y direction would be the normal force and then this component of gravity that we're going to call FGY. So we're going to call up positive, down negative. So we're going to say Fn minus FGY has to equal, and we're going to say 0 because the block isn't accelerating up or down. So MA goes to 0. So that allows us to solve this equation, and we're going to say Fn is equal to FGY. And we know FGY is going to equal mg cos theta. Now the reason for this, I can draw it out. I drew it out over here. I'm going to expand this triangle. We know FG, if it has components, that the FG part has to be the longest part of the triangle, right? So so when you're thinking about the components, you're not going to extend this FGY to be all the way down there and be the longest part. No, because its components are derived from FG. So none of its components can be bigger than FG itself. So oh my gosh, this thing likes to mess with me. So here's FGY, here's FGX, and here's theta. You might be asking, well, why isn't this theta? Because it's not. Simply because it's not. I could go through the whole derivation, and if you'd like me to, I just say in the comments. I'll go through it in another video. But it's just you can go through it yourself, do some geometry, and then connect the triangles. You'll see that this theta, the theta that is from this triangle, is that theta, right? So now let's think. How do we get FGY from FG? Adjacent and hypotenuse cos theta gives me adjacent, which is FGY, over hypotenuse, which is FG. Great. FG cos theta equals FGY. MG cos theta equals FGY because FG is MG. Done. That was a little quick. I can go through it more if anyone would like, but yeah, just let me know. But that's basically it. So the normal force has to be equal to the y component of gravity, which is mg cos theta. So now we're going to go back into our friction equation. And now we know that since friction is mu Fn, the friction is mu mg cos theta. And I actually made a mistake here because the entire time I have it's 2 mg. So it's 2 mg. Because what's it called? This little thing up here, it was 2m. It's 2m. So it's going to be 2 mg cos theta. I like making that mistake. I don't like me. I just do it a lot. So all right, next question. Let's sub in what we got. So 2 mg. I'm gonna put the mu cos theta times d is equal to 1/2 2m final squared minus 2mg d sine theta. So earlier I said I left the 2m for a reason, and you're about to see that reason is because it's on every single term of my equation on both sides, I can cancel it. So there's 2m here, there's 2m here. Like for example, if this one didn't have 2m, I can't cancel it, right? That's just how math works. So now I'm going to rewrite this with what I know. So I'm going to go g mu cos theta d is equal to v final squared divided by 2. I just combine these two to get this term. Minus 2d sine theta. Oh, not 2d sine theta. D sine theta. All right, next one. So now we're going to add d sine theta to both sides. So d sine theta minus g mu cos theta d. Now we're going to multiply. We'll just say v final squared 2. And now we're going to simplify fully, but we're going to also take this d out because it's in both terms. So we're going to multiply by 2 and factor out that d. And we're going to get sine theta minus mu cos theta. And we're going to take the square root in order to get the final. And as a matter of fact, I just like to check if that's correct. Because now I'm doubting myself. Let's just see. Here we go. Okay, I'm not leading you guys astray. Oh, I'm actually an idiot. So D sine, you may have noticed this, but I dropped a G here on accident. So it's 2. The G is supposed to be there. Otherwise, everything else was right. So yeah, so that G came from up here. I just forgot it here. But on to the next question. That took a little long. Here we go. So let's go to part II. And it says, derive an expression for the spring constant K of the spring. This might seem like a hard question. It's not. What you need to realize is that there's going to be some energy. So the velocity we have here that we just derived, which is this, gives us the kinetic energy of just block A. After they collide, they lose kinetic energy. So we're going to have to find the new kinetic energy by going through momentum, right? After the collision. And then we can say, well, the kinetic energy of the two blocks as it compresses the spring is equal to the final spring potential energy. So I'm going to show that now. And then we can find K. So we're going to say after the collision, P final has to equal P initial. We're going to start there, right? So our V final here is actually the V final after it like smooths down the ramp. It's actually going to be our V initial for the collision, right? Because it's at the end of the ramp's motion, but it's at the beginning of the collision's motion. So we're going to say our initial momentum is 2m. We're going to say v naught. And we'll sub in our v naught. 2m square root 2g d sine theta minus mu cos theta. And leave it like that, right? So this is just mv. Now let's say, what's the final momentum? Well, since the blocks stick together, we're going to add their masses and treat them as a system. We're going to call it 3mv. v as in like the final velocity. I'm just going to leave it as v. Now I see m on both sides of this equation, so I'm going to cancel it. And I'm going to divide by 3, and we get 2/3 of square root 2gd sine theta minus mu cos theta equals the velocity, the new velocity after they collide. So now that we've done that, we can say E final equals E initial for the spring part. This laptop likes to mess with me. So the initial energy was kinetic energy. So 1/2, and remember these blocks are 3m now, v squared. So this is the kinetic energy, all goes to spring potential energy. This is the spring potential energy equation. So I'm going to cancel the 1/2 because it's on both sides. So now I'm going to sub in that v that we had earlier, which is right here. So what is, but it's v squared, right? So what would v squared give us? Let's think. 2 squared is 4. V squared is 9. If we have anything inside a square root, we just take the square root off when we square it, at least. And this is v squared. So we're going to sub that in there. So it's going to be 3m times this entire monstrosity of an expression minus mu, oops, cos theta, a lot of parentheses, is equal to kx squared. Now, this is looking nice, right? Because we don't have any more unknowns. We have m, we're allowed to have m because it says express terms in terms of m, theta, d, mu, and xc. And k is the only unknown, which is what we're trying to find. So we don't even, that's what we're deriving, right? In essence. So now we can, where is this? So now we can just solve for k and simplify a little bit. So we're going to go 4m. And then I'm going to divide 3 on both of these, and that'll give me 4m over 3. And we're going to take this x squared and put it in the denominator of the other side so we can get k by itself. Times 2gd sine theta minus mu cos theta. Sorry, let's go back. Let's fix that. Minus mu cos theta. Is that right? Equals k. And you could just leave it like that. This would simplify to 8/3 because of that 2, this 2, but I'm not going to do that. Next question, but that's how you get the spring constant. And you may have not seen that, but it's all right. That's what the practice is for, right? You're here now, you're looking at it, and you'll see it on the exam, probably. So on the following axes, sketch a graph of the magnitude of the momentum PA of block A as a function of time. Oh, so sketch the momentum as a function of time from time 0 to time 4. Okay, so we really just have to think about the momentum equation. So this is our momentum equation. So basically, m is a constant. We literally just don't have to care about that. All we have to care about is how v changes, right? So let's think about it. At time t equals 0, this block from t equals 0 to t equals 1, that has a constant acceleration. And you might be thinking, well, no, it doesn't because of friction. No, friction just decreases the acceleration from what it would be if it was just pure like gravity, right? So the acceleration is a bit less than mg sine theta because mg sine theta is fgx, which causes the x acceleration. So it's less than that because of friction, but it's still constant. So if you remember from kinematics, if you have constant acceleration, then you have a linear velocity. So our momentum here is going to follow the trend that velocity does, and it's going to be linear. Now from time t1 to t2, it's not doing anything. It's frictionless, horizontal, no forces acting on it. Object at rest will stay at rest, or in motion. If it's at motion, it'll stay in motion. So there's going to be nothing happening there. The momentum won't change. And if you're confused on why I'm treating velocity as momentum, I mentioned earlier, P of t will act like V of t because m is just a constant that'll just scale things up, right? So now from t equals 2 to t equals 3, we have to think, how will the velocity change? Well, the velocity will drop by roughly 2/3, like we showed up here, right? Here's the 2/3, and here's the initial velocity. So all we have to do is show 2/3 of what it was before. Done. And after that t equals 2 to t3, no other forces are acting on it. It'll stay like that. But now here, this is a little bit interesting. You might be thinking, oh, it's linear. Well, no, it's not, because the spring force is negative kx, right? Meaning it varies. It'll be kind of like this. And you're asking, well, why is it concave down? Why isn't it concave up? The reason why it's concave up is the acceleration is getting increasing. Like, A is equal to dv dt. If I look at the slope of this graph, it's going to get bigger and bigger and bigger, right? It's going to get more and more negative because the spring force is getting more and more larger because F equals ma, so F is related to A. All you have to understand is that it won't be concave down, because if it was concave down, that would mean the spring force is going to 0. It's not, because if you compress a spring more, everyone knows it's going to push back on you more. So let's see the next question. It says, using... Oh, I hate this. I'm not going to torture you guys with my handwriting. I'm just going to talk about it. Use principles of forces to justify the graph from time interval t equals 3 to t equals 4. Okay, so we just did that. The graph will be concave down. So we're going to reference the figures, concave down and non-linear as A as the spring force will increase with t, making dv dt making the slope steeper and not making the slope steeper and graph the concave. And then you'd also want to throw in a little portion that, well, it's nonlinear, so since the spring force is nonlinear, that means velocity will also have to be nonlinear. Or sorry, the spring force is linear, so when you take the integral of a linear thing, it'll give you like x squared, so it'll have to behave like that, because you know the integral of a dt gives you v. But yeah, we'll leave that there. If you have any other, you can ask questions in the comments. I'd love to answer them. So yeah. For times t is greater than t4, the two-block spring system oscillates with period TO. The procedure is then repeated using a new ramp where there's negligible friction between block A and the ramp. Also, it oscillates. Okay. So it's repeated using a new ramp where there's no friction. Well, I'm going to answer this by saying Tn equals To. The reason for that is because it's a spring, right? We have to think about the period of the spring, which is 2 pi square root m over k. Now, do I see initial velocity anywhere in this? No. So because v naught is not proportional to t, t will not change. Also, m, and k are constant, hence t will also be constant. There's your justification. And you might be asking, why am I thinking initial velocity? It's saying negligible friction. Well, the initial velocity would increase if you have less friction, because there's less energy dissipated. More energy can go into kinetic, more velocity. There you go. Next question. Wow, sorry if I'm taking long, guys, but here's two. A student drops a sphere of mass m from rest. The air exerts a drag force of magnitude F drag on the sphere. As shown in figure 1, the student models the magnitude of the drag force as F drag equals bv, where v is the speed of the sphere and b is a positive constant with appropriate units. Derive but do not solve a differential equation. So do not solve. So derive a differential equation that can be used to determine speed v of the sphere as a function of time t. Okay, I know this. So all you have to do here, whenever you see derive a differential equation and you see drag, sum your forces. Let's think about our free body diagram. F drag is going to act up, well, act in the upwards direction because velocity is downward when it's falling, right? It shows you here too, F drag is falling. So they have to be in opposing directions. So the sum of the forces on the y is we're going to call our direction of acceleration down, or positive, minus Fd equals ma. And now a, since a is equal to dv dt, this is a point. They give you a point for subbing in dv dt. You're going to sub in every value because fd is bv, fg is always mg, equals m dv dt. There we go. Oops. And we can leave that like that. That's our differential equation. You could solve this. They might ask you to this year. Good luck to you if that happens because I take way too long to derive mine, but it'll be all right. So yeah, this is, since they only ask for the differential equation, that's the differential equation. Differential equations usually have something like this: dv dt, di dt, dl dt, something like that. Not dl dt, we don't vary out like that, but yeah, usually you'll see something d dt. So let's go to question B. The student sketches the drag force F drag exerted on the sphere as a function of time t as shown in figure 2. Draw a vertical line on the sketch in figure 2 to indicate the earliest time at which F drag is equal to the magnitude of the weight of the sphere, which occurs when the sphere reaches terminal speed. Label this time tt on the axis. Okay, I'm going to draw that out. So FD and then t, I'm going to draw it like this. So the key here is that knowing that when V terminal is reached, V isn't changing. So dv dt has to equal 0. And you know that since F equals ma, right? Whenever force drag is no longer changing because force drag is dependent, sorry, because you can use F equals ma or you can F equals bv, fd equals bv. Since fd is dependent on v, when v reaches a constant value, fd reaches a constant value. And that happens, my drawing is bad, but the moment that this graph goes like horizontal, that's when tt has occurred. I'm gonna label that there. Okay, justify. Okay. When vt is reached, v of t is constant. Fd is proportional to bv. When v is constant, so is fd. The force of drag. So that's basically what I just said. I'm just putting it on paper. Let's go to C. Let's see. Suppose the student throws the same sphere downward with a non-zero initial speed. The magnitude of the new drag force at terminal speed after being thrown is F nu. Indicate whether F nu would be greater than, less than, or equal to the magnitude of F drag at terminal speed. So he's saying he's throwing it down instead of letting it fall. I'll tell you right now the answer is equal to, because, so we're going to write equal to. We're going to think, what is terminal speed? Because we have to derive it. At terminal speed, if velocity isn't changing, acceleration is 0, right? Because dv dt, the rate of change of velocity, would be 0 because it's not changing, making ma equals 0, making some forces equal 0. So some forces equals 0, which has to equal mg minus bv, right? The gravitational force minus the drag force. So that means the forces are equal. Because it says, oh, okay, yeah. So my justification, I was just wondering, my justification up here is when they're equal. You can say that because they're equal, when terminal speed is reached, they're equal. Just write that in there if you didn't. So the forces are equal when terminal speed is reached. So I'm going to label that VVT. And you can derive this here and say mg divided by b gives you vt. So here's my answer. So when mg, because mg and b constants, and not dependent on V naught. V of t will be the same in both scenarios, and if Vt is the same, Fd will be the same. Will be the same. Therefore, F nu equals Fd. Does that make sense? So because the terminal velocities will be the same, the maximum drag force will be the same. Wow, I am running out of space. It's okay. Okay. If you guys don't mind, I'm just gonna. I honestly thought I would have more space for this entire thing, but no, it's okay. Yeah, so if you want to see that, just go back, rewind the video, and yeah, let's get on to the next question. Part D. The student conducts an experiment to better understand the relationship between F drag and V. The student takes measurements to calculate the graph and the magnitude of F drag as a function of V. This falling sphere. Okay. Draw a line of draw a line of best fit for the data. So I can't do that here because I don't have my I guess overlay up. But the way you would do that, I'll go through this question. I did it in my earlier video. I would recommend you go look at set 1 to do this. But the way you would do this is you find the line of best fit and you take its slope by picking off 2 points, right? So you pick off 2 points, and after you pick up 2 points, you find slope, which would be equal to F, the change in the drag force, over the change in velocity. And the way you would utilize this slope is in this next part where it says II, use the line of best fit to calculate an experimental value for B. You would use the fact that, where is it? Sorry. Yeah. You would use the fact that F drag is equal to BV and recognize that this is a linear relationship, y equals mx. So your slope would be B. So whatever slope that may be, the slope that College Board gave me is 15 newtons minus 5 over 21 minus 5. So that would roughly give you 0.625 kilogram per second. So yeah, that's basically what you would do here. You would find the slope, and that slope would be your B. That's it. Use this fact that they gave you earlier. They said FD is equal to BV, and then you can just leave it there, right? And if you want more clarification on that, I recommend you go look at the first set 1 video that I made on this 2024 Physics C pre-response guide, and I do it more detailed there. So let's look at E. The student claims that the terminal speed Vt of the sphere depends on the diameter d of the sphere. The student designs an experiment to collect data that can be used to provide evidence to support the claim the student has access to, but does not use. So he has access to sphere set 1, known mass, different known with different diameters, same diameter, and different masses. So he wants to prove that the terminal speed is dependent on the diameter. Okay. And it says indicate 2 quantities that one graph could be used to determine whether the diameter of the sphere affects the terminal speed. So we're going to say, intuitively, you should just be thinking on the vertical, you'll plot terminal velocity. On the horizontal, you'll plot diameter, right? And the reason for this is because because you only want one variable, because if you want to change a single variable, um, there's not a multitude of different variables that could be causing a change in terminal velocity. If you have one variable, you can pinpoint the fact that like if this, you can state that if this changes, right? If this stays constant, this stays constant. But if you have diameter and mass, varying. Well, you don't know which one is causing the change, so it would just be diameter. And the students want to figure out whether diameter depends on the speed. So just, I would put these two. So briefly described how the quantities graph could be used to determine the relationship between the sphere diameter and terminal speed. If VT changes with the relationship, else no dependency. Done. Next question. Dang, I'm gonna keep having to clear this because I'm running out of space. Okay. Oh, this is a torque problem. Okay. A uniform disk of radius r and mass md is attached to a vertical pole and by a horizontal axle that passes through the center of the disk. Friction between the axle and the disk is negligible. A lump of clay of mass mc attached to the edge of a disk at point A. Oh, is attached to the edge of the disk at point A. The size of the lump of clay is small compared with the radius of the disk. So with that statement, with this, they're telling us that the rotational inertia of this little mass can be treated as a point mass. So you can use mr squared. That's what they're saying, right? That's the entire point of this statement. All right. A horizontal string is connected from the pole to the edge of that disk, to the edge of the disk at point A. The string makes an angle theta with the line between point A and the axle. Okay. On the following representation of the clay disk system, draw and label the external forces, non-components. Oh, so it's asking for a force body diagram. This is really bad. I can't draw circles. I'll just do it here. So draw and label the forces acting on this. Okay. So the mass of the clay causes a gravitational force. I'm going to call FGC, which is equal to mcg. Tension pulls inward, as always. Right? Why would we be pushing outward? Tension pulls. And the disk has mass md. We're going to call that FGD. And since this disk is not moving, in order for, what's it called? It to be at equilibrium, there has to be another vector, another force there called F pivot. You may be asking, well, why is it up? Why is it not down? It's because in order to balance the forces that are already down, right? These are the two forces. There's two gravity forces. It has to be extremely up in order to cancel these. And why is it to the right, not the left? Because tension pulls to the left, and it has to cancel that by going this way. So it's going to be to the left, up, that way. That's a little clustered, but yeah, you get the idea. Okay, so there's your force body diagram. I don't think I missed anything. No, yep, because it says uniform disk. So center of mass is at the middle. So B, derive an expression for the tension Ft in the string when the clay is at point A, as shown in figure 1 in terms of R, Md, Mc, and theta, and physical constants is appropriate. Okay. So the way we're going to do this is we are going to sum our torques because the torque there it's not we wouldn't sum forces, we're going to sum torques because it's the forces are being applied at a radius, right? So we know that our sum of torques has to equal 0. And let's list them out. We have the torque due to the force of tension. We're going to use our right hand rule, and it's radius cross force, tension. So the torque due to the force of tension is positive, which is counterclockwise, but the torque due to the gravity of the clay is going to pull down, making a clockwise torque, which would be negative, right? And then the only other two torques, the only other two forces act at where radius equals 0 or where there would be no torque, right? Because the pivot force produces no torque because it's at the axis of rotation, and gravity is at the axis of rotation, no torque. So now, using that fact, we can set the torques equal to one another because their sums are equal to 0. And now we refer to our basic torque equation, radius cross force. Radius cross force. And now what's the radius for these two? The radius for both of the torques is r. So it would be r ft. And now we're going to think about how this ft, would it be sine theta or cosine theta? This is what we need to ask ourselves, because we have to take the two vectors, this is the radius vector and the tension vector, and put them tail to tail, right? So I'm going to redraw it like this. Now they're tail to tail. And this theta, alternating interior angles, is that theta. So the angle between the two is sine 180 minus theta. So this, because you remember in torque, when you're doing a cross product, you want the theta, or a cross product or a dot product, you'll do sine or cosine of the theta in between the two vectors you're multiplying. And that would be 180 minus theta, which is just sine theta. So it would be sine theta, not cos theta, right? But now we're going to look at the gravity vector. So we're going to, again, take the two vectors. Here's gravity this time. We're going to put them tail to tail. And our theta earlier, where was our theta? It's here, alternating interior angles, right? There's theta. And here's a 90-degree angle. You're asking why? It's because I drew parallel lines and used the facts from geometry to say that these two thetas are equal to one another. And these two, this is normal to that. That's perpendicular to that. So that gives me 90 degrees. So this theta, this angle is the angle between the two. So we're going to take the angle between the two, which would be 90 plus theta, right? You see that 90 plus this angle here, 90 plus theta, which is cos theta. So we're actually going to write for our right side RFGC. Remember, FGC is the force of gravity acting on the clay. Cos theta, not sine theta. So we're going to cancel our r's because it's on both sides. We're going to say FT equals FGC cosine. We're going to divide by sine on both sides to cancel it here. Cosine divided by sine is cotangent, but we don't get to leave it in terms of FGC. We got to derive FGC, which is the force of gravity acting on the clay is mcg. That's just like a general physics thing. Force gravity is always mg, and the m would be mc. So here's our force tension. Leave it like that. Question, part C. The string remains connected to the edge of the disc at point A. Clay is moved to point B, which is horizontally in line with the axle. How does the new tension? Okay, so they're going to leave the string where it's supposed to be, and they're going to move the clay so it's horizontally in line with the action. So the tension, how does the new tension compare to the old tension? Intuitively, we're going to think the torque when it was up here was not at its maximum because it was at theta. But when it's here, it is at its maximum because the sine of theta, if I take these two vectors again, put them tail to tail, here's this one's tail, here's that one's tail, I'm going to move that over here. We're going to get like this. Sine of 90, that's the angle. This is the angle between the two, is 1. That's the max. So we're going to have a larger torque. So larger counterclockwise or a larger clockwise torque in order to keep equilibrium is going to require a larger counterclockwise torque. So we're going to say force tension new is greater than force tension because moving the clay to point B increases the torque it produces to maintain some torques equals 0 if TFGC increases, TFG, or no, TF, sorry, must also increase to account for the change. My handwriting's horrible, sorry guys. Larger torque, larger FT. There you go. And that's the answer for that one. Let's move on to the next question. And I'm going to have to erase this. But yeah, the general idea, more torque in the clockwise direction has to be more torque in the counterclockwise direction in order to keep it at equilibrium. Larger counterclockwise torque, larger tension because radius won't change, right? I would write that radius won't change. But generally, I think they'll get the idea. So let's move on to part D. A non-uniform disk is now attached to the axle. The lump of clay is attached to the disk at point B, shown in figure 3. Oh, okay. So the lump of clay it's now at point B, and it has mass of 0.60 kilograms. And the disk has radius 30 meters, and the mass density of the disk is modeled by rho r. Rho as a function of r is equal to br, where r is the radial distance from the axle, and b is equal to 4.0 kilogram meters cubed. And it's asking us to find the rotational inertia of the disk about the axle. So I disk, which is rotational inertia about the disk, is equal to integral r squared dm. That's pulled straight off your equation sheet. I can find it up here, right here. This is rotational inertia. Because the mass density is non-uniform, we're going to integrate in order to find that. So we have to think our rho is equal to difference in mass over difference in volume, right? Or well, it's rho, but it's a disk, so we're going to say difference in area, right? So now we're going to say, okay, the area of the disk is equal to pi r squared, right? Because if it's a disk, they're not giving us the height of the disk, like the thickness, so we can say it's a area mass density. So the area is equal to pi r squared. So the difference, the dA in area is 2 pi r dr, right? So now I can say that rho dA, which is equal to rho 2 pi r dr, is equal to dm. Now I can sub that dm in for this one, and let's take that over here to do that. So now we're going to integrate from r squared to rho, and rho was br, so we're going to substitute that in. Br times 2 pi times r again, dr. And we have to integrate from where radius is 0 to radius is maximum, so 0.3, because we have r's in here, and we're taking an infinitely small change in radius, so we're going to integrate from our limits 0 from where radius equals 0, radius equals 0.3. So we're going to take all our constants out. B 2 pi integral r squared times r gives me r to the fourth, dr 0, 0.3. And now I can plug this in my calculator because they gave us b, so it's going to be 4 times 2 pi, right? And I could integrate this manually, and I will, because r to the fourth gives me r to the fifth over 5 from 0 to 0.3, which is essentially 8 pi 0.3 raised to the fifth divided by 5. And we're going to use decimals for that. So let's see. 8 pi 0.3 raised to the fifth divided by 5. Roughly 0.12214 kilogram meters squared. There's our rotational inertia of the disk. Oh, 0.012. There we go. All right. That's because it said calculate, not derive. We can leave it like that. Now I. So the string connecting the disk to the pole is cut. Calculate the magnitude of the initial angular acceleration of the clay disk system. So what you should be thinking here, angular acceleration, torque. What causes the angular acceleration? Torque. We're going to use Newton's second law in rotational form. Sum torques is equal to the rotational inertia total of the system times the angular acceleration. And the only torque after the string would be cut is the torque due to the force of the gravity of the clay, because the string is no longer providing a torque, it's just the clay. And it says initial, so we don't have to think about, well, the theta is changing, so we have to integrate. No. It says initial, just think when sine is 90. So we're going to use our torque equation, R cross F, G, C. And like we said earlier, that's RMCG sine 90 because it's initial. So initially when it's cut, the sine is still at 90. It's 1, we can ignore it. And now we have to think, well, what's our I total? Because we have these values. We'll sub those in later. But what's I total? So I total has to equal the I of the disk plus the I of the clay. Because the clay is still, it has mass, right? It's still important and it still contributes to the rotational inertia. So we know the I of the disk, like we just calculated, was 0.12214 plus, and earlier I had mentioned that they said the size of the lump of clay is small compared to the radius of the disk. That's them telling us we can treat it as a point mass. So we're going to use mr squared, the mass of the clay, which was 0.6, times the radius at which it's at, 0.3. Plug that into our calculator. I'm just going to add on to our earlier calculation because it's the same thing. Squared gives us the total rotational inertia to be 0.662. Here we go. 0 point, is it there? Yeah, it is. Roughly 0.066214 kilogram meters squared. And now I can plug in all my values to find the initial angular acceleration. So we're going to do that. 0.3 was the radius. 0.6 was the mass of the clay. Gravity is 9.81 divided by 0.066214 is my angular acceleration. And we're going to say that's roughly equal to, we'll put that in decimals, 0.6, forgive my handwriting, 0.066214 gives us roughly 26.668 rad per second squared. Never forget your units. And that's the answer. All right, I hope you guys, well, I guess enjoyed this video, but enjoyed hearing me talk about physics. And I hope that you guys will do good on your exams. I'm looking forward to mine, surely. I'm still taking the class, but we actually just wrapped up mechanics. We're on, I think, capacitors, but who knows? But yeah, good luck to all of you on all your exams, and I'll be seeing you in the next video. You have a nice day.